Newton's laws of motion. In this little presentation we're going to look at all three laws of motion, just talk through them quite basically, give you enough information that you need to know really for this exam, and then we're going to look at the equation as we look at Newton's second. There's one equation you need to know, and right at the end we'll just talk about what we mean by terminal velocity. Okay, Newton's first law, this is it. A body will move at a constant speed in the same direction, or it will remain stationary unless an unbalanced force acts on it. Let's just put this in a few different ways because that can be quite confusing. Objects keep doing what they are doing unless some force, sometimes not easily seen, changes either their speed or direction. So if you're going at a constant speed, you'll end up staying at a constant speed unless a force acts. If you're sliding along the floor, then you will slow down because a force is going to act. That force is friction. So Newton's first law sometimes is quite difficult to see or appreciate when we are governed by friction. But if you take friction away, when you saw the air track in lessons, which is the thing with the little holes in, where the little black trolleys sort of float above the air track, then we sort of tried to remove friction, and it did look as though those air tracks trolleys would keep going forever. So objects keep doing what they are doing. Another way of saying it, objects which are changing speed or direction must have a force. So if your speed is changing or your direction is changing, you've got a force acting on you. And also objects with all forces balanced may be moving with a constant speed or be stationary. So that is sort of different ways of saying what at first looks at quite a complicated law. Let's just quickly look at balanced forces and see if we can apply Newton's first law in a couple of situations. Here we go, someone on a bike. This is kind of an old gentleman on a bike. He's pedalling away. If we show some forces, we'll be able to see that the forward force, his thrust, is equal to the air resistance and friction. I know that because I'm sort of adding up the lengths of the arrows. If you add that arrow and that arrow, it's about the same length as this arrow. And you can see he's going at a constant speed. So all the forces are balanced. The forward force is equal to the backwards force, and also this thing called a reaction force of the ground is equal to the weight of the bicycle down. So the bicycle's not moving up or down, it's sort of stationary in the vertical direction, and it's going at a constant speed in the horizontal direction. So this is a good example of Newton's first. We'll just do a couple more. Here is a parachutist. If we show some forces, the weight of the parachutist is equal to the air resistance upwards provided by the parachute. Balanced forces moving at a constant speed. And finally, this satellite in space, something out in deep space. It's not in orbit, so it's sort of going way out the gravitational pull of any planets. Is it moving? It looks as though it is. Show the forces. There are no forces because there's no gravity, there's no thrust. This is just going at a constant speed in a single direction, and there are no forces on it. So no resultant forces is acting, but it's still moving at a constant speed. Newton's second law relates force, mass and acceleration, which we looked at in the last lesson. Little silly pictures, but nice to think about. In which picture would the acceleration be higher and why? So we've got somebody with a small force pushing somebody with a larger mass, and here we've got probably somebody with a larger force pushing somebody with a smaller mass. And from the pictures, gives you a hint. You can see that the acceleration in this picture is higher, and this is because we've got the largest force and the smallest mass. In this picture we've got the smallest force and the largest mass, so we end up with the smallest acceleration. Let's just put some graphs on this based on the work you did in lesson. If you increase the force, if we keep the mass constant, so if we keep the mass the same, if we increase the force, the harder you push something, the faster it will move away from you. Its acceleration will increase, and it does this at a proportional amount. A proportional graph means a constant slope, and it goes through the origin. So if we double the force, from 2 to 4, we increase the acceleration from 1 to 2. So this is a proportional relationship. So this is like our first, it's like our first picture. Okay, let's look at this graph. This is mass and acceleration. Here we are keeping the force constant, but we're increasing the mass. So if we push a mass with the same force, but then see what happens as we increase the mass we're pushing, we'll notice quite obviously that the bigger the thing we're pushing, the less acceleration we get. So this ends up with a curve downwards. As we increase the mass, the acceleration is decreased. If we really looked at this graph, if we doubled the mass, if we go from 2 to 4, then we've halved the acceleration, because we've gone from sort of 5 down to 2.5 there. So doubling the mass halves the acceleration. This is what's known as an inversely proportional relationship. Let's tie it all up then. Let's combine the two ideas that we've just looked at. The larger the force, the greater the acceleration. This is a proportional relationship, but the bigger the mass, the smaller the acceleration. This is an inversely proportional relationship. We combine all that together and we say that acceleration is proportional to force, but inversely proportional to mass. So acceleration becomes equal to force divided by mass. You're given this equation. You're given it in both formats, or you can rearrange this equation and say that force equals mass times acceleration. This is sometimes called F equals ma. You might have heard in lessons. This is Newton's second law. Let's just do a couple of example questions. I've got a formula up here to help. We've got a cyclist of mass 60 kilograms, rides a bike of mass 20 kilograms. When starting off, the cyclist provides a force of 200 newtons. What is the acceleration? We can use this equation as it is. Acceleration equals force divided by mass. So acceleration equals 200, the force, divided by the mass. Note the trick. You've got to add up the mass of the cyclist and the bike. So 60 plus 20 is 80. 200 divided by 80. Shove that in your calculator. You get an acceleration of 2.5 meters per second. Okay, a little bit harder. Question 2, probably a higher level question. A car of mass 500 kilograms is travelling at 20 meters per second. The driver sees a red light and slows to a halt. That's 0 in 10 seconds. What force must the brakes provide to do this? We've got to do 2 steps here. We need to work out the acceleration, or it's actually a deceleration, but let's just call it an acceleration. The acceleration is change in speed divided by time. So we've gone from 20 to 10. Sorry, we've gone from 20 to 0. So 20 down to 0 is a change in speed of 20, and we've done it in 10 seconds. There's the 10. So 20 divided by 10 gives us an acceleration of 2 meters per second. We're not done now. The question asked us what force must the brakes provide. Here I'm going to rearrange this equation to force equals mass times acceleration. We've got our mass, 500 kilograms, so we can put that in, and we've got our acceleration that we've just worked out, 2. So we multiply those together and we get a force of 1000 newtons.